Good afternoon, class. So in today's video, what I'd like to do is to go over torque. And so in this one, this is the rotational equivalent to force. However, this is where we all get a little bit, where everything gets kind of counterintuitive, okay? There is a lot that I can do here where it doesn't seem to make sense unless you've actually experienced it before. So one of the examples that I like to do is I'll tell a student, hold this, and I will push with my finger over here, and then I'll let go, and then I'll push over here with my finger, and as you can see, I can bend this pretty easily. This, if you can kind of see my knuckles, if I press over here, I can resist. My hands are getting kind of, tired and sore, but that's fine. But if I double that distance and I start pushing even more, notice I can barely hold on, and notice how much more effort this fist is actually putting in to try and resist the rotation. All because I changed that distance. So that is the example of this R value, the distance, and it's a vector because it points in a direction from here to here. So it's pointing in this direction. Now, this video is going to be a little bit more on the intermediate to advanced side because there are vectors that are involved. So I thought I would separate that part just by telling you this part over here is more for intermediate to advanced physics people, or people who are more curious towards how do you see what college level physics would be like. If you're more on the basic level of physics, don't worry, I have your equation right over here, which is tau equals RF. Okay, so don't worry about that. However, if you're on the more advanced side, you're interested in seeing this in maybe a college course or maybe a more advanced course than this, then this is the equation for you, because torque is actually a vector quantity, and it is the cross product between the fulcrum or the distance vector and the force vector. And of course, where do I get what happened to all of my notations over there? Why is it RF sine theta? That's because that's the determinant of that matrix. So when you have cross products of vectors, what it is a matrix multiplication. And so in order to find the determinant of that, you would get, this is the result that would come about from that. I skipped a whole lot of steps for those of you who are far more advanced in physics, so feel free to check that out and look that up. I wanted to keep this video relatively short and still appeal to both levels of physics. So keep that in mind. That's where this is coming from. And this cross product, by the way, is actually where everything starts to go wrong with your intuition, because you have really, you and me and everybody in this world, all physical beings, generally have a very hard time conceptually understanding the cross product because it moves in a direction that you don't think. For example, let's take a bicycle tire. The force on the bicycle tire actually points outward. So if you think, if the bicycle tire rotates in this direction, and it has the spokes going this way, the force is actually pointing outward towards the camera. And that makes no logical sense, at least to our physical minds, because we don't see that force vector coming out. So I thought I'd point that out as a little thing to get you interested in what is going on. And by the way, if you do want to see some videos on how bicycles work or how we don't know how bicycles work, just type that into a Google into a search either on YouTube or on Google, and you'll see it. You'll see it. People have done videos on how bicycles work. What I thought I'd do is I would show you some of the differences or the difference that this R vector can make in this video. So you've got all the lecture portion of it. You've got the academic side. By the way, for all of the basic physics students, the part that you need to know is that tau is equal to RF, and the reason why is because that angle is always going to be 90 degrees, or pi over 2. So my example would be something like this. If I wanted to bend my arm like so, I'm going to apply the force at a 90-degree angle like this. Then that will bend my arm. that is for the basic levels. Now, for the more advanced students who are thinking, wait, a theta doesn't have to be 90 degrees. You're right. It could be at an angle. I could be putting an angle like this and getting that rotation. I could be doing all kinds of things. So what I thought I'd do is to show it using a shoulder stretch. And since I have my meter stick, I thought I'd use that to help me out. What you do is, if I grabbed it, now notice my arm can bend about this far naturally, okay? So what I'm gonna do now is I'm gonna grab it here, go back to my natural length, and then I'm gonna start pulling on it. And notice, all I'm doing is I'm using this hand over here to pull this to, I can stretch my arm further. Now, I don't wanna go too much further because that could break my shoulder. But notice, if I go over here and I start pulling, hopefully you can see it kind of in the way my muscles are straining and on this hand right here, that I'm pulling a lot harder and I'm not getting as much of a stretch on this hand right over here. However, if I increase the lever arm and I pull, this side isn't even pulling that, this side isn't even getting pulled that hard versus this side is getting pulled quite a bit. So I can actually extend my arm and stretch out my shoulder quite a bit by doing something like this, even though I'm not putting as much effort in with my other hand. So, thought I'd demonstrate that to show you what forces can look like. Now, obviously, if you want some better demonstrations of this, let me know in the comments below, and I'll try to do some, because the thing is, Brazilian Jiu-Jitsu is actually a really good demonstration of torque. You want to see how all the submissions play out using torque? Let me know in the comments below, and I will do my best to try and have them demonstrated in future videos. So that's it for this video. Good luck in your studies, and I'll see you in the next one.